Here is the thing almost every summary of MemRL gets wrong. It is not a full memory controller. It is not an agent that learns to store, forget, and consolidate end-to-end. It is something narrower and more important. MemRL is a runtime, non-parametric retrieval and valuation policy over episodic memory. The model weights never move. The memory itself becomes the thing that learns. Every memory the agent holds is formatted as a strict triplet with 3 components. You have the intent, the experience, and a utility score labeled Q. Welcome back to Bearded AI Guy. Today I am walking through a capstone analysis from the human architect on this precise architecture. This matters now because the 2026 agent stack is converging on one hard question. Agents need memory, but the real fight is about where adaptation should live, inside the model's weights, in a learned controller, or somewhere else. MemRL picks a side. It proves that a completely frozen model can adapt purely by using environmental reward to re-rank its historical experiences. To see why MemRL is distinct, we have to look at the 4 memory regimes currently in contention. This matrix maps weight plasticity against memory plasticity. Static RAG and ReasoningBank rely on semantic similarity, assuming proximity equals utility. Conversely, Memory R1 and Agentic Memory apply offline fine-tuning directly to model weights. MemRL is distinct, uniquely applying runtime learning strictly to external memory metadata. The atomic unit of this architecture is essentially an index card. It records what the agent tried to do, what actually happened, and a score representing how useful reusing that memory has turned out to be. This diagram shows the data pipeline the system uses to filter index cards. It is a 2-phase retrieval process. Phase A handles similarity recall. The system uses a standard cosine similarity threshold to pull an initial broad batch of memory candidates. Phase B introduces value-aware selection, governed by this equation. The system re-ranks the initial candidates by calculating a weighted blend of their normalized semantic similarity and their accumulated utility score. The ablation study finds the optimal weighting occurs when lambda equals 0.5. An equal blend is required. Pure similarity plateaus because it cannot filter out distractors. Pure utility fails because it detaches from the user's specific query. MemRL evaluates historical agent utility against the current context through a learned ranking function, rather than relying on raw text retrieval. When the agent attempts a task and succeeds, or fails, the neural network itself undergoes 0 changes. Instead, the system simply nudges the utility score on the injected memory up or down, based entirely on the task's final outcome. This flowchart illustrates the runtime loop. The engine driving the change is a Monte Carlo update rule applied to the Q-value. Here, the learning rate alpha is 0.3, and the discount factor gamma is 0. The authors provide mathematical proofs that this update method maintains unbiasedness and bounded variance. But those guarantees strictly require 2 assumptions: a permanently frozen inference policy and a strictly stationary task distribution. Requiring strict task stationarity is exactly the mathematical boundary where MemRL's theoretical guarantees will break in a real-world production environment. That brings us to the primary vulnerability of learned memory systems. They struggle when tasks lack shared structural elements. This chart compares MemRL against a single task reflection baseline. If every problem is structurally unique, the utility estimates have nothing to latch onto. You end up with a cache of high-scoring memories that completely fail to generalize. The systems tie on the HLE dataset specifically because HLE has low internal semantic similarity. The learning fades when the tasks diverge. The second major vulnerability is reward hacking. Realistic evaluations by Anthropic show that models capable of reward hacking exhibit a 12% sabotage rate, actively undermining detection. Multi-memory updates also suffer from credit assignment ambiguity. If 5 distinct memories are injected and the task succeeds, the algorithm struggles to isolate which specific memory actually earned the reward. If an agent's reward channel is gameable, runtime learning becomes a liability. It will computationally amplify and validate the wrong patterns deep within the agent's memory substrate. Because runtime learning is vulnerable to reward hacking and credit ambiguity, it cannot be the only memory layer in a production system. By 2028, we expect to see a layered architectural stack to handle these trade-offs. For enterprise support or coding, where task similarity is high and verifiers are dense, this runtime learned layer becomes the standard for performance. However, in regulated environments, this layer must sit beneath a provenance and version control capstone. Production requirements for strict traceability prevent a purely autonomous, utility-based memory from acting as the final authority. Transfer data justifies this layered approach. MemRL achieves a held-out transfer success rate of 0.794, outperforming baselines like MEMP at 0.766. Memory utility works across task boundaries, but it needs a safety harness. MemRL serves as a clearest proof that memory value must be treated as an isolated, inspectable, version-controlled policy surface, separated entirely from the model weights. For years, the default assumption was that improving agents required continuous post-deployment fine-tuning of the model itself. MemRel reframes that. You leave the model alone and move the plasticity dial one layer up, directly into the operational memory cache. Memory operates as an active substrate with its own feedback loops, functioning as a layer of live state rather than a static database. The core engineering question for 2026 shifts. Stop asking how to make models remember better. Start asking where in the stack adaptation belongs and what exactly you are willing to let it change. If this kind of careful read of a single paper is what you came for, subscribe to Bearded AI Guy. I go deep on one piece of the agent stack per episode. Drop a comment below challenging one of the technical vulnerabilities we discussed, whether it is the verifier trust argument, the credit assignment ambiguity, or the 2028 hybrid forecast. All of this analysis comes from the human architect, whose work in the book AI Agents in Action served as the stress test environment for these theories. The memories an agent keeps inherently form a policy. The only question is whether you chose that policy or inherited it. I will see you in the next one.